All right, so let's continue and practice some more with logarithms. So let's use the properties of logs to expand the following expressions. The first one, we have ln of 17 times x squared, right? So according to the rule, when we have times, this is going to turn into ln of 17, the first quantity, plus ln of x squared. Okay, so when we have times, we have addition. Furthermore, we can say that this equals with natural log of 17 plus, we're going to use the exponent rule that allows us to bring the 2 in front of the log. So this is going to be plus 2 times natural log of x. So here you go, this is the answer. We have expanded ln of 17 times x squared, and it equals this. For the next one, you notice that we have ln of a quantity divided by another quantity. So we're going to use the rule that tells us to subtract the logarithm. So it's going to be ln of x to the 4th minus ln of that whole bottom, y cubed square root of x, or z to the 7th. So now, furthermore, I can use the rule for the exponent and bring this exponent down. So this is going to give me 4 times ln of x minus. Now in this right here, I have ln of a quantity, which is y cubed, times another quantity. So I can furthermore use the property that tells me that this is going to turn into ln of the first quantity plus, because this is multiplication, ln of the second quantity. So now, furthermore, I distribute the negative, so it's going to be negative ln of y cubed, and the negative gets distributed to this one as well, so minus ln of, remember, rational of exponents, when I have square root of z to the 7th, that means that I have a 2 in here, and this turns into z to the power 7 over 2. So recall when we had square root of x, that was x to the 1/2, basically because we had a 2 in here and then a 1 in here. So now if we have square root of z to the 7th, this is going to turn into z to the 7/2 power. So now we have these exponents, and using the rule, this is going to allow us to bring the exponents down in front of the log. So the final answer will be full natural log of x minus 3 natural log of y minus 7/2 natural log of z. So we expanded this, and this is the answer. So we're just using the properties of logs. All right, let's do one more. This one is a straightforward one, so it's going to be log of 7 minus log of x, because we have division and we subtract when we have division. All right, so we can be asked to do the reverse. So we have it in an expanded notation, and we're asked to rewrite it as a single logarithm. So basically we're doing the reverse of what we just did. So since I have log of 22 plus log of 1 over 11, this is the same as saying log of the first quantity times the second one, right? Because when we had times, we had plus. So now this is going to turn into log of 22 times over 11 is just 2. Okay, so we're doing exactly the opposite. And now for this one, notice I have a log of x minus 2 log of y plus 1/2 log of z. So the first thing, we're going to take care of this and bring it back as an exponent, and then take care of this and bring it back as an exponent. We're doing everything in reverse. So it's going to be log of x minus log of y squared now, and then plus log of z to the 1/2 is square root of z. So now I have minus. So when I have log of a quantity minus log of another quantity, that's going to turn into a log of the first quantity divided by the second quantity. So that's just for these two. We combined these two into this, and then plus log of square root of z. So now I have plus, so I'll have to multiply the two quantities. So it's going to be log of x over y squared times square root of z. So I can just put it at the top there. So see how we had it expanded and we contracted it. We wrote it as a single log expression. All right, so all the problems, word problems that we're gonna deal with are going to ask us to solve for something. So we better get good at solving log equations and exponential equations, and then when we have the word problems, we're gonna have a good time solving those because we know how to solve equations, so we're gonna apply them to word problems. So for the first one, I have ln of e to the x equals 21, and I'm just gonna apply rules. That's all I'm gonna do. So this is the exponent, so it's gonna come down in front. So this is gonna turn into negative x times ln of e equals 21. But ln of e is 1, right? This equals 1. So basically what I have is that negative x equals 21. So x equals 21. That will be the answer. Now, I'm solving for x. So when you're asked to solve an equation, you're asked to solve for x. So I need to isolate the part that has the x. So I need to isolate this part. So this 2 right here, this negative 2 right here bothers me. So I'm going to add 2 to both sides. So I'll have 10 to the x equals 100. And then if 10 to the x equals 100, basically 10 to what power gives me 100? Well, I know that 10 squared gives me 100. So that means that x equals 2. Okay? All right, now we got to solve for y. And so I'm going to isolate the part that has the y. So this 5 right here is bothering me. So I'm going to divide both sides by 5 first. So I'll have 10 to the 4y equals 31 divided by 5. And what do I do now? So I have exponential with base 10. And y is an exponent, and I got to solve for it, right? So if I can't directly solve for it, like if it's not obvious what the exponent should be to get that, it's not obvious what the exponent, what y should be, such that when I do 10 to the 4 times y as an exponent, I get this, then we got to think about logs, to apply logs to both sides. So I'm going to take log of both sides, okay? And now I have the rule of exponents that allows me to move this exponent in front of the log. So now I'll have 4y, the whole exponent comes down in front, times log of 10 equals log of 31 over 5. So I applied log to both sides. If I do something to one side, I needed to do this so I can bring the exponent down, I better do it to the other side. But now log base 10 is just 1, because 10, remember if the base was not there, it means it's 10. And 10 to what power gives you 10? 10 to the first power. So this is equal to 1. Equals to 1. Alright, so now I'll have left 4y equals log of 31 over 5. Since I'm solving for y, I'm going to divide both sides by 4. And the answer will be that y equals log 31 over 5 divided by 4. So this is the exact answer. Exact answer. And then if we put it in our calculator, we're going to get the approximation. So let's put it in our calculator. So it's going to turn log 31 divided by 5. And then I close the parentheses for the log, and then I'm going to divide the result by 4. And I get that it's 0.198. So the approximation is y equals 0.198. The approximate answer. Okay. All right. So what about this one? I have the log. If the base is not there, it means it's 10. It's 10. Of x equals 4. So I have to rewrite this in exponential form. So since the base of this log is 10, because it's not there, I'm going to say 10 to what power gives me, so 10 to the 4 power gives me x, right? Because it switches the input and output. So the output, the 4, goes as input for the exponential, and the input, which was x, goes as output for the exponential. So this gives us that x is 10 to the 4, and that means that x is, well, it's 10,000. So we solved it. What about for this one? I need to solve this one. So I'm first going to divide by 9. So then I'll have log of x equals 18 divided by 9, which is 2. So now to rewrite this in exponential form, I know that the base is 10 because it's 10 right there if it's not there. So 10 squared equals x. So x equals 100 because 10 squared is 100. All right, so now let's solve some word problems and apply what we just learned. So let's say you have a pot of boiling water with a temperature of 100 degrees Celsius and set in a room. The temperature of the water after X hours is given by this equation, and you notice that you have a exponential in there. To estimate the temperature of the water after 2 hours, we basically have to plug in x equals 2. So after 2 hours, when x equals 2, I'm going to have 20 plus 80 times e to the negative 2 because x equals 2. So if we put that in our calculator, it will be 20 plus 80 times e, so e is right here on the division, to the power negative 2. And you hit enter and you get 30.83 equals 30.83, and this is a temperature, so it'll be degrees Celsius. So if you leave this pot of boiling water in a room, it's going to reach 30.83 degrees Celsius after 2 hours. So we were given what x is. It was 2 hours, and we found the temperature when x is 2 hours. So now, what about this other question? It says, how long did it take for the water to cool to 30 degrees? So we are given the temperature now that it's 30 degrees, and we're asked to find x. And notice that x is an exponent, so we're going to need logs to solve for x. So the temperature is 30, so this equals the temperature after a certain x. So T of x equals 30. So I'm going to set it equal to 30. So 30 equals 20 plus 80 e to the negative x. And now I got to solve for x. So I'm going to subtract 20 from both sides. And I'll get that 10 equals 80 e to the negative x. Since I got to solve for x, I'm going to isolate the part that has the x. So I'm going to divide by 80 now. So I'll have 1/8 equals e to the negative x. So I isolated the part that has the x. Now I notice that x is an exponent. So to bring it down, I have to apply logs. We can apply ln, natural log, because the base is e. So I'm going to take ln, apply ln of both sides, because this is going to allow me for the exponent to come right in front of the ln. So we will have ln of 1/8 equals negative x times ln of e, but ln of e is 1. So basically this gives me that x is, it was negative x equals that, so x will be negative ln of 1/8. So this will be the exact answer. And when we put it in our calculator, we'll get the approximation, negative ln of 1/8. 2.08. So x equals 2.08 hours. So after 2.08 hours, the water cools down to 30 degrees. So make sure you notice the difference when we are given x and we're asked to find the temperature, opposed to when we are given a certain temperature and we're asked to find for what x that happens. Every time we're asked to find a variable, an unknown, and that unknown is at the exponent, we're going to have to use logs to bring it down and then get the answer. All right, let's do one more example. We have that the number of fish in thousands X years after 1975 can be modeled by this equation. Okay, so we're going to estimate the year when the number of the fish reached 93,000. So we need to find the X such that the output is 93,000. So I have to set it equal to 93,000 and then just solve for X. So I'm going to divide both sides by 221. So then I'll have 93 over 221 equals 0.873 to the X. So now I need to solve for X because X is going to tell me when it reached 93,000. So to bring the X down, we have to apply log of both sides. And notice that in your calculator, you only have log or ln. So pick one of them and that's the one you're going to apply. So let's do log this time. So I'm going to take log of both sides. So it's going to turn into log of this equals log of that. So I'm doing the same thing to both sides. Because when I do logs, I'm going to use the rule that allows me for the exponent to come down in front. So therefore, we'll have that log of 93 divided by 221 equals X times log of 0.873. So since I'm solving for X and X is multiplied by this number, I gotta divide both sides by that number. Because when I divide both sides, this is gonna go away. And all I have left is that X, right from here, X equals this number. So X is log 93 divided by 221 over log 0.873. So this is the exact answer. And if we put it in our calculator, we're going to get the approximation. So go to your calculator. So we're going to be careful, log of 93 divided by 221, close the parentheses, and this is divided by log of 0.873. So 6.37. So X equals 6.37. So this one is the exact answer and this is the approximation. So after 6 years, let's round it to 6. So in 1981, since X means years after 1975. So in 1981, the population of this fish is going to reach 93,000. All right, so let's just set up the next one. It says estimate the year when the number of fish halved. So if they halved, they started with 221. So I'm looking for when it reaches 221 divided by 2. So you're going to do the same thing we did on part A to solve for X. You're going to isolate the part that has the X. So you're going to divide by 221 both sides. And then you're going to take log of both sides and get the time when the number of fish halves. What about if we're asked to find the year when the number of fish decreased to 30% of its initial population? So it started with 221. So we all decreased to 30%. Basically, I need to find when the population is 0.3 times 221. Because 30% of what it started with means you multiply by 0.3. So again, we're going to solve this by dividing by 221 both sides. So we'll get 0.3 equals 0.873 to the X. And now since X is an exponent and we're solving for it, I'm going to take log of both sides. so that I can bring the exponent down in front. So then it's going to be log 0.3 equals x times log 0.873. So x is going to be log 0.3 divided by log 0.873. So this will be the exact answer, and when I put that in your calculator, you get the year that the population reaches 30% of what it started with. All right, I lied, we do have one more example. So the last example is when we start with C grams, so they don't tell us what we start with, but it says that whatever this substance starts with, it decays at a continuous rate of 10.2% per year. And the first one is to create a model that represents the amount A. So A after X years is going to be A after X years. It's going to be C, whatever it is. Since it's continuous and it's decay, we're going to use that e to the KT, right? Because every time we have continuous, we got to use this formula. So it's going to be e to the, well, it's 10.2%, so it will be 0.102 x, not t. But since it's decay, we got to put, negative. Okay, so this is the formula we're going to work with. C times e to the negative 0.102x. To answer the other questions now, determine the number of years it will take for the amount of substance to decrease to 10% of its current amount. So basically, I don't know what it started with. So if it started with C, what should I put on the other side if I'm interested in 10% of what it started with of C? I'm basically just going to put 0.10 times C. Okay, because I'm interested, I don't know, if C is 100, I'm interested to see when it decreased to just 10. You think about that. Pause the video and think about that, why I put 0.10 times 10. So now you'll see that I can divide both sides by C, and then I got that 0.10 equals e to the negative 1.0x. And since I'm trying to solve for x, because I'm trying to find when it decreases to 10% of what it started with, I'm going to take natural log of both sides because I have the base e in here. And this is going to allow for my whole exponent to come in front right here. So basically what we'll have is ln of 0.10 equals the whole exponent comes down in front of the ln, but ln of e is 1. So then to solve for x, since it's multiplied by negative 0.102, I need to divide both sides by that. So then this goes away with that. So on this side, I'll have x equals this. So this will be the exact answer. And to get the approximation, we'll put that in the calculator. So it's going to be ln of 0.10, doesn't make sense, divided by negative 0.102. So it's 22.57. 57 years. So it takes that many years for this substance to reach 10% of what it started with. So you see, we don't need to know what it started with. We just need to know when it reached 10% of whatever it started with. And now for C, after 17 years, there were approximately 407 grams of the substance remaining. So let's write down our equation. We have that A of x, the amount left after x years, was CE to the negative 0.102x. Now it says after 17 years, that means that x is 17, and then there were approximately 407 grams left. So this, the amount left was 407. So our equation becomes 407 equals c times e to the negative 0.102x. Oh, 17 instead of x. And it says, to the nearest gram, how many grams of the substance were initially present? So they're asking you, what is c actually? So we're solving for c, and notice that c is multiplied by this. This is just a number, and this is just a number. So to solve for c, I gotta divide by this number, both sides. There's no need for logs in here. We're not asked to solve for an exponent. We're asked to solve for c, and c is already down where we like it to be. So then c, this goes away with that. So c is going to be equal to 407 divided by e to the negative 0.102 times 17. So let's put that in our calculator. So it's going to be 407 divided by, let's put the whole denominator in parentheses, e to the power, and at the power we have negative 0.102 times 17. And then come down and close the parentheses. And we get 2304. So let's see, let's round to one, not one decimal, let's round to the nearest integer. So 2305. 2305 grams. So if after 17 years we have 407 grams, it means we started with that many grams. Okay? So guys, the reason we learn logs is because when our unknown, what we're interested in is an exponent. To solve for the unknown when it is at an exponent, we need to learn logs so we can bring the exponent down. All right, so that concludes the logs.